So these processor flags in our EFLAGS register keep the status described as condition codes or status flags. And the condition codes refer to the information that most recently were updated by the instruction that was executed. So in other words, when this last addition instruction just before we return executed, it updated the flags according to the results of the arithmetic that was performed. So for example, if decrementing a register becomes 0, the value of flag 0 flag is set by the processor. So a programmer might say 0 condition has occurred. So each flag is a single bit in flags register. So it's shown here in the register display of Visual Studio as EFL, but its official name is EFLAGS. If last addition or subtraction produced a negative result, a sign flag will be set, right? So this will be, we'll be able to apply our mask and find out if this is non-zero, then the result of this mask should tell us that the sign flag is set. So we can observe the results by doing some simple command executions in our immediate window. So this is the result of sign flag. For instance, if it's set, it means that the value, the result of the last arithmetic operation was negative, and if it's cleared, which is 0, then it means that the result was positive. So that's the way you can interpret the results in the flags. The carry flag. The carry flag is a very important flag, and with arithmetic addition and subtraction, the carry flag represents the 9th bit if we manipulate 8-bit numbers, the 17th bit for 16-bit size values, and 33rd bit for 32-bit numbers, and so on. If our data type keeps growing, it's just one additional bit in the arithmetic. So with addition, the carry flag records a carry out of the higher order bit, of course, right? So if we move -1 into AL, we know that AL will be set to all ones because bitwise the 2's complement -1 is all bits set to 1. And if we add 1, then we should have a result that the AL will become 0 because this is the rollover to the higher value, and the carry flag will be set to 1. Okay, so we can perhaps we can try this just to observe how our masks work and how the carry flag is being updated by these manipulations. So I'll just say debug, stop debugging right now, and just add a couple of instructions like this directly from our presentation right here. So let's take a look. Probably we can just set a breakpoint right here if you'd like and say debug. Perhaps we build first because we made an update, and then debug, start debugging. Right, so we run through the program. Our console window, of course, is not interacting with us because we're just using very little amount of instructions in the program. But in our debugging environment, we can still make observations. So let's watch the results of EAX. And the AL, of course, is the lowest portion right here of AL. So -1 should appear as, we step over F10, as FF. Of course, this is all bits set to 1 in the lowest portion of EAX, in this last byte of EAX, which is available through mnemonic AL. So then we say, let's add 1 to AL. And notice that the move instruction, unlike arithmetic instructions, does not update the flags. Okay, so we can move without destroying any flags. However, the next arithmetic instruction, another add instruction, which adds 1 to AL. So let's observe what happens. We just press F10 one more time. We step over, and you see that the result is that register AL is now set to 0, and look how the flags were updated, right? So the flags were updated. So let's take a look, right? So we take a look at the EFLAGS. So this is now 257 hexadecimal. So I'll just replace it right here. If you try this on your own, just remember that because this is a C notation inside immediate window, just use prefix 0x in front of hexadecimal value. And if we want to analyze the carry flag, right? So we just apply this expression right here. I'll just clear everything in this window and copy and paste this, and you see that this time the carry flag is set to 1. So the result of the value in AL previously set to all ones, we are adding one more, so everything is becoming 0, but the carry out of the highest bit inside this 8-bit register AL that resides directly inside EAX is that we have a carry flag, and of course this indicates unsigned value overflow. Now also, because the result of this addition is that this register became 0, 0 flag should also be set, right? So if we already figured out that the mask for 0 flag in the 6th bit inside our EFLAGS is 64. So we just take this here, right, and we just say, okay, how about this? So we just go here and take a look at the 0 flag. So copy and paste, hit enter. So it returns 64 because the bit was set. So if you want to see 0 or 1 here, we need to do something like this, right? So we need to take this in parentheses and say, as long as it's not 0, then display the result, right? So how about we update it like this? All right, and that shows us true. It means that the 0 flag is set, right? The 0 flag is set here, simply because yes, indeed, the AL register resulted in 0 as a result. But the carry flag is set, so nothing is lost, really, because in case of AL example like this, this is 8-bit value right here, right? And the carry flag simply becomes the 9th bit for arithmetic manipulations. So here, yes, we just proved that both carry flag and 0 flag were set to 1 as a result of this last arithmetic instruction. So when a larger number is subtracted from the smaller one, the carry flag becomes a borrow, just like we do in decimal arithmetic. So when we do it on paper, we say we can borrow from the left position to the left position when we do this type of arithmetic. So here, if we update our program, we can observe that if we take 6 and subtract 9, the result is -3. So the sign flag should be set because -3 is negative, and the carry flag is also set to 1 because we had to borrow, right? 6 minus 9, we had to borrow from someplace, so the carry flag should be set. So we can try this, of course, and as well in our debug mode. So once again, let's just say debug, stop debugging, and we'll try this again. Okay, so just this time we try to observe the flag results with the subtraction. Okay, so we'll just move to, I guess we just save, build quickly, and I already have the breakpoint here. We can move the breakpoint down to this line, press F5 to start debugging. Again, the program is running, so we're just updating AL to 6. So we just step over. This is 6 right here. You see that AL is now set to 6 because we just did this. And now we're subtracting 9. All right, so we just press F10. And the result of it is that, of course, this became FD, which is obviously, you know, if we want to see what FD is, we can go back to our immediate window and say 0x and FD, and you see that the result is the positive value is 253. Okay, but of course the negative value is -3. So apparently this immediate window shows the result by default. It shows the result is as unsigned value, but we know that this is also -3 if you look at this. So the sign flag should be set. So let's verify it. So our flags now are 293 hexadecimal, so I'll just update it right here. Yes, it's very tedious, but sign flag is mask is 128, so this is what we have to do to be able to work with this. And we say as long as it's not 0, we should see the true or false for this flag to be set, right? So this is new expression that I will just copy and paste into my immediate window. I can just clear it before I do this, so that it's just clear to see. And yes, it's true, because of course if we interpret the new value of AL as 2's complement number, it's a negative number, it's -3. So this is why the sign flag is being set as a result of this instruction subtract. The carry flag should also be set because in unsigned world we would have to borrow from the left hand side of 6 in order to be able to subtract 9. So let's take a look at the carry flag. So we just simply update our mask to 1, right? So we just repeat this expression right here, copy and paste and hit enter, and yes, so the carry flag is also set as a result of this. All right, so these are examples of how arithmetic instructions such as add and subtract update the flags. All right, so the flags are being updated by every arithmetic instruction, and they provide the status, the result of the arithmetic that we just attempted. So a lot of CPU instructions update the results in the flag register of x86 architecture.